Hello, I am Matt Eland. This is a supplementary talk for the Central Ohio.net Developer Group, or CONDG, which I'm an organizer of. I am Matt Eland, or at IntegerMan on Twitter, which is a great way of getting a hold of me. During the day, I am a software engineering instructor at Tech Elevator, where I teach C# development to new professionals looking to get into the development world. It's the best way of getting to tech I've ever seen, so if you're curious about that or know somebody who is, check us out. We're awesome. But this talk is about ML.net, and specifically using ML.net's automated machine learning libraries, or AutoML, to predict video game ESRB ratings for games that have not yet been released. The core of this talk is really going to be about AutoML and what we can do with that, what that is, and what that gets us as developers. So when I'm not teaching, I am off making YouTube content and articles around data science concepts, especially around ML.net and Azure Machine Learning Studio. So check me out if you're interested in that. Give me a subscribe as well. It always encourages me. In my ample spare time, I am off pursuing a Master's of Science in Data Analytics through Franklin University, where I hope to graduate in the fall of 2023. And that will enhance my ability to teach data science concepts to newcomers. So this talk today, I'm going to focus a little bit on what machine learning is, just so you have some basics associated with you, just so you can understand the rest of this talk. I'm going to get into what ML.net specifically is, and then even deeper what AutoML is within ML.net and what that gets us. We're going to look over some sample automated ML code as we look over a car MSRP prediction program. That's going to be an example of regression, and we'll talk more about what regression is in a bit. And then the bulk of the talk is going to be focused on using multi-class classification in ML.net's automated ML to predict ESRB video game ratings. And we'll close with a brief discussion of how you can get started with ML.net and what are some good resources available to you to get started. Okay, so let's briefly talk about what machine learning is, so you're not hopelessly confused for the rest of the talk. A machine learning model is essentially a calculator. It takes in a set of inputs and it spits out an output. Those inputs could be something like a historical set of car prices or a historical information about video games and what ratings they received. But it's been calibrated to receive a certain type of inputs, do some calculations based on its trained model, which we'll talk more about what that means in a minute, and then spit out an output. That's all machine learning is. It's effectively a giant calculator. Now, the cool thing about machine learning is that we can use statistics and mathematics to optimize our machine learning models to learn patterns hidden in our data so that they can have accuracy comparable or perhaps even better than a human. And that's really helpful when we have a massive amount of data flowing into our applications and we don't have enough people to be able to analyze it in real time, where it's not economical for us to be able to do that. Additionally, there's some places where we might find a machine learning model is better than a human in many cases for detecting things such as cancer detection and other fields. So that's really the core of machine learning in a quick moment there. But at its core, we take in a set of features, we feed them into our model. The features, again, could be something about car prices or whether or not the video game has alcohol and violence and things like that. We feed those into our model, and we get back a label, which is just a machine learning term for a prediction. So features are data or pieces of data that are unrelated to the thing that we're predicting, and labels are the one specific thing that we are trying to predict. So just some machine learning terminology there, labels and features. Some things about the model training process. So training machine learning model is very slow. That's something that has to be done and evaluated by, well, at least with human involvement at the moment. So a machine learning run might take anywhere from 10 seconds to several days, potentially in a really large model. You might even be using distributed processing to take care of that. So training a model is not something that you might do in real time as data is coming in. You might do it on a nightly basis, but you're not going to do it all the time. Okay, and again, once we train that model, a human has to validate that the model performs well enough. For example, if I made a machine learning model to predict whether or not a mole was cancerous, and my accuracy rate was 55%, that's just a little bit better than a coin flip, right? So that might not be a model that I might want to deploy and use and have people's lives depend on it. So you need a human to review your model for performance and see how it's doing before you might even think about deploying it. Now, on the other hand, once we have our trained model, that's when we can take in predictions in real time. Our models perform very quickly because really they're just transforming an input into an output using some pre-trained pathways. And so it's very high performance, especially in ML.NET. ML.NET is built around performance. You do, however, have to monitor your models just to make sure that they are still relevant as time goes on. For example, if I built a machine learning model to predict the price of a car that might come onto a resale lot, well, that might be accurate for a little bit, but as inflation and car markets change, my predictions, if they're based on old data, they're not going to be very helpful to my organization, so I need to monitor them for what we call data drift and potentially replace them with a more up-to-date model that's been trained on more recent data. So that's really the difference between training a model and deploying the model for use in predictions. So important difference, but that's the difference. So let's pivot into what ML.NET is. So ML.NET is a machine learning framework by Microsoft. They released it in, I think, spring of 2019. It is open source. It is cross-platform. It's built on .NET standards, so you can use it in any type of .NET project, whether that's going to be, let's say, Xamarin or UWP, Blazor, traditional web applications, a console application, unit test project, whatever it might be. It's going to be supported in almost anything you might do with .NET, and that includes C#, F#, and VB. So it's very, it's a very ubiquitous thing in Microsoft's ecosystem. It is free, which is awesome. It is open source, as I mentioned. It is very high performance, so it's built to have a very high degree of performance as you're predicting things. Training things, everything in machine learning takes time as you train. That's okay. It is actually very open as well. So it supports something called ONNX, or ONNX, and that is a format that we use for the open exchange of neural network information. And so we can take models that are built in TensorFlow, for example, and import them into ML.NET and run them in C#. We can take our ML.NET models and we can export them to this format, and then other things can use them. So ML.NET is a model citizen in the data science world, and you start to be able to see this trend where we might train our models in one language and use them in another. Well, with ML.NET, we can train our models in C# and use them in C#, which is great because many web servers are running on .NET technologies. But we can also take a pre-trained model in TensorFlow or something else and import it into ML.NET and be able to run with that. So that's awesome. It is also worth mentioning that ML.NET is used internally by Microsoft, I believe in many of their Azure offerings, but I don't have the specifics as to which ones use it or which aspects of it are used. So the question that naturally comes up when we're talking about ML.NET is, well, wait a minute, why does Microsoft have to have their own ML.NET thing? Why can't we just use Python or R or Julia or TensorFlow JS or whatever it might be, whatever other machine learning libraries or languages are out there? Well, it's true that there's a very vast amount of community support for Python and R and other data science languages. But they're not exactly running our web servers, are they? They're not exactly running our production applications. There's a lot of production applications out there on ASP.NET. Well, ML.NET runs on those technologies, and so if you ever want to deploy a machine learning model, well, you just put it out there on your web server. You don't have to write a new one in Python or add a new web service out there just to represent your model. So we can integrate our machine learning models directly into our production applications and work with them there. You also can take advantage of existing skills. Your .NET developers don't necessarily need to go out and get deep knowledge in R, for example. So there's a lot of advantages of using ML.NET, and there's certainly nothing against Python or R or Julia or JavaScript or any of these other things you might use to use machine learning. Those are completely valid, and I personally love training machine learning models in Python and working with data science in Python as well. But ML.NET has some very applicable bonuses when we get to deploying things to production and using skills that people might already be specialists in. So let's talk specifically about the process of training a model using AutoML within ML.NET. So AutoML is a subset of ML.NET. It's an area of it that's really built around the automated training of machine learning models for people who might not have deep knowledge of all the various machine learning algorithms. Okay, so as you're starting out in data science, you don't have to know the ins and outs of the algorithms being used and the hyperparameters they require. You're just going to go out, pick the right one for your task, and then work with it. So the flow for this is we start out and we are going to just load some data, either from a database or from a CSV or some other form of data. We're going to load it into what we call an iData view. This is kind of like a data frame that we can work with. It's a set of columns. And then we create a machine learning experiment to represent the type of task that we want to do. And then we take our experiment and we run it. We run it for a prescribed amount of time. We'll talk about the right parameters for that later on. And when that's done, we have a trained machine learning model. Now we then need to evaluate how well that model performs to see if that's something we want. But if we like it, we go ahead and we save it to disk. It's going to actually create a zip file for that model. If we don't like it, well, we tweak the parameters around our experiment. We might try giving it a little bit longer to train, or we might give it slightly different data. We might do something else, but we might tweak a couple things. But AutoML really shines in this part right here. Well, actually these two parts. So it's configuring the experiment, and then it's trying all sorts of different machine learning algorithms and hyperparameters for that algorithms to see what performs the best. So I might run my algorithm, I give it 10 seconds, and it's going to try a whole bunch of different things, and it's going to settle on the one it likes the best. Right? That's the idea behind AutoML. It makes this a lot more accessible for people who don't know the ins and outs of data science. Now, once we have a trained model, whether that was built using AutoML or not, we can then work with it in the traditional ML.NET way. So we can load that model from a zip file, or if we already have it from training a second ago, we can just work with it without having to load it up. But we can load something from a zip file on a production server, and then we can create what we call a prediction engine, and that's just a pipeline that's going to take in some sort of inputs and spit out some outputs. And then once we get in new pieces of data, we can make predictions around that. So this is really what machine learning is all about, is we've memorized some historical patterns in our data, and using those patterns that we've sort of baked into this model, we're now able to predict new values. For example, if I have a bunch of historical information about cars and how much they've sold for based on their mileage and features and things like that, my machine learning model might be able to estimate the sale price of a new car that's come onto my lot that I'm evaluating whether or not I want to buy and resell. So this is the value of machine learning, is we can predict things based on historical trends, and these might be patterns that a human hasn't even noticed, but a machine has. Okay? So at its core, ML.NET is really working with models, and ML.NET calls these models transformers, and it designates these via use of the iTransformer interface. The data that we load that into an iData view. It's usually a data frame, but it implements iData view. And what we do is we feed our data view full of features into our model, our iTransformer, and we get out a specific result. And that's typically going to be a single result, but it might be multiple. So the machine learning model just takes in the data for the features, it transforms it into the output with the prediction. That's kind of what we're doing with ML.NET and AutoML. So let's take a look at what AutoML is. When most people hear AutoML, they initially think of something called the model builder in ML.NET. The model builder is something that you can use if you install a specific extension. So if you go into your Visual Studio extensions menu, so I think that's Tools, Extensions, and then Options or Store or whatever, and you can search for ML.NET or Model Builder. and you should find ML.NET Model Builder for whatever version of Visual Studio you're using. I'm running 2022 Community over here, but it's available in most, I think, since 2017, but I'm not sure. But you'll be able to work with that. You can install that, and once you install that, you have access to the Model Builder. Now, I'm not talking much about the Model Builder today, but it's useful for context on what I'm talking about for the rest of today. So Model Builder is a way where we can say, hey, I'm going to right-click my project, I'm going to add a machine learning instance, and then I'm going to choose what task I want. I'm going to give it some form of data. I'm going to tell it to train for a certain amount of time. And it's going to try all sorts of different machine learning algorithms, and it's going to identify the best one by the end. And once we're done, we'll have a trained machine learning algorithm, which we can then look at some performance metrics and even just generate some code for that and add it to our project automatically. So that is the Model Builder. It's awesome, but it has some limitations, which we'll talk about in a second. The same capabilities are also available via the command line interface. If you wanted to mess around with that, you really have the same thing. Now, the interesting thing about this is that these technologies are both powered by the AutoML API, and that's what I'm going to be talking to you about today. That's what I want you to learn, because we can write our code directly against that AutoML API, and we don't need to use a tool, we don't need to use CLI, we don't need to install an extension. We're just working with AutoML directly. So it has some advantages directly over Model Builder. We don't need our Visual Studio extension. It's just .NET code, and we can just work right with it. We can create an application to train data and tweak the parameters of that as we need to, as our needs change. We can pass it off to another team member, and they can run it without any other knowledge. But it has some other advantages. So the Model Builder and the CLI will generate a new project for you. They will not just generate a file in your current project, if that makes sense. So it's sort of something you do once at the beginning of your project. It has some shortcuts for like retraining your model on new data, but it's not really the same thing as like retraining it from beginning. And so you need to sort of do the Model Builder periodically. And AutoML, working directly with the API, it's a little faster to work with the API than just trying to build a Model Builder using the same parameters you used a month ago or whenever it might have been. And so it has some advantages there. You can also incorporate AutoML directly into any other .NET code, so you can conceivably put it into an endpoint in your in a protected web service or something like that. And when you make it an authorized call to that web service, it might train a new model and store that model for later evaluation. However, Model Builder does have some upsides. You don't have to write code, and it can also do more things. So AutoML's API only supports 5 basic tasks of machine learning. Now, 2 of those are the most common things that you're going to do in machine learning, or 3 of those, but it only supports 5, versus the Model Builder supports a few other things. So what are we losing? What are we losing support for? Well, we don't get the ability to do clustering in AutoML yet. We don't have the ability to do time series forecasting, anomaly detection, image classification, which really is through Azure anyway, or object detection. So these are things that we can't do yet in AutoML. But we're getting there. It's improving over time. But what can AutoML do? Well, it can do most of what you want to. Most of what you're doing in machine learning, at least at the beginning, is you are doing a classification run, where you're determining what category something goes into, such as whether or not a mole is cancerous, whether or not a loan approval should be approved or rejected, something like that. The ESRB rating of an unreleased video game, that's a classification problem. The other one that you're doing a lot of is regression. That's where you're predicting a numerical value. So we're predicting the sales price of a car, of a used car, for example. That might be an example of regression. You have a couple of more edge casey things with recommendation and ranking. So recommendation is based on user preferences. What would a user like me like that I haven't seen before? This is the kind of thing that's powering Amazon and YouTube and even Twitter with some promoted tweets and hey, the people who liked this also tended to like that kind of things. Ranking is very much like recommendation, but it's not segmented by users. It's where you just have a forced order rank of things, and based on this ranking, hey, here's some new data. Here's where I think this would fit into your pre-established ranking categories. So recommendation and ranking are a little bit more rare to do, but they're powerful capabilities. So today's talk is primarily about classification. I did a classification task a while ago where I was getting into an interesting discussion with my wife about whether or not Die Hard was a Christmas movie. And so I built a classification model to learn patterns in historical movies and whether or not those movies were Christmas movies. Well, a classification problem here, this is a binary classification, is whether or not a movie is a Christmas movie. So if my trained model knows all about Christmas movies and non-Christmas movies, but knows nothing about Die Hard, when I show it Die Hard, what does it think Die Hard is? Is it a Christmas movie or is it not? Spoilers, it's a Christmas movie. But that's a different talk. Classification use a confusion matrix, which is confusing at first glance. But this is kind of really just a checkerboard where you have a value that you're predicting. So we're predicting, in this case, maybe we're predicting it's a Christmas movie, or we're predicting it's not a Christmas movie. And in this case, we might have made 65 predictions that it was a Christmas movie that turned out to actually be true. This movie actually was a Christmas movie. So this is an accurate value here. But sometimes we predicted things were Christmas movies which didn't wind up being the case. In this sample data, this is just a sample I got from Microsoft, not actual data from any of my projects. But this is a case where we predicted it was something, maybe cancerous, maybe a Christmas movie, whatever it was. We were predicting it was something, and it actually wasn't. There are cases where we predicted it wasn't something, but it actually was. So that's a false negative. There are the cases where we thought it was and it was, that's a true positive. The cases where it wasn't and we thought it wasn't, that's a true negative. And then over here we have a false positive. We thought it was true and it was actually false. So with a confusion matrix, you want your items to be along this diagonal. You want them to be in this tile or this tile. When you see results in other tiles, that's little inefficiencies, little places where it's wrong or mistaking things. So those are generally bad. You try to get as few of those as possible as a higher performance model. This is going to be relevant later on as we discuss ESRB ratings, so I'm going into a little bit more depth with the confusion matrix. But let's shift gears again, no pun intended, sorry, and talk about MSRP prediction for cars. So if I'm running Matt's used cars a dealership, I need to be able to price some data. So we'll take a look at what this process looks like. Well, the first thing we need to do is get some historical data about cars and car sales. So whenever I'm looking for any sort of data, I go out to Kaggle.com. And Kaggle.com is a free data science community. You can go out there, click on data sets over there on the little menu sidebar, and just do a search over here. I did a search for car MSRP, and I found this data set. I saw that 539 people liked this data set quite a bit, and so I just downloaded it, right? It's a 1 megabyte file. I downloaded it, I added it to my application, and I can see information about the data in here without even having to download it. But I have information about the make, model, year, fuel type, horsepower, city and highway mileage, things like that. But I have a CSV file now, and this has historical data, and it has information here on the MSRP. And that's important. I need labeled data, so it needs to have the historical MSRP of cars that have already sold. So what I do is I added it to my project. So I created a data directory. I don't have to create a directory, but I thought it was helpful to organize my project. I copied in my car data.csv into this project. By the way, this is just a console application. I was just doing something simple for demonstration purposes. I changed the car data CSV to copy to output directory if newer. So whenever I build my project, it's going to make sure that this car data CSV goes out into the output directory of my project. This is important because I want to refer to it based on the program's directory. You don't have to do that, but that's what I did for this particular demo. Next thing I did is I went in and I added references to Microsoft ML. So if you right-click on the project, you click Add New Packages, you can then go in and search. I searched for Microsoft.ml, and I installed the latest version of Microsoft ML AutoML. I also installed Microsoft.ml. You don't really need to do that because AutoML also installs it, but I feel a little bit better with both of them installed. And that gives me everything I need for my experiment. Okay. So I have the data in my project. I have ml.net now referenced. Next thing I do is I need to create what we call a model class. The model class is just a plain old C# class. So we have public class car info. I can call it whatever I want. Doesn't really matter. Car info is intuitive for me. I usually call these things something ending with info because that's good for both training and prediction. The name makes sense there. And then I need to basically tell it all of the columns I care about here. So I'm telling it column 0 in this data set is the make. Column 1 is the model. Column 2 is the year. Column 3 is the fuel type. And we're going in here by index. This is one of the things I hate the most about ML.net is having to build these models. I actually saw an extension while I was creating these materials for this presentation about a model generator extension. So I'm interested in checking that out. That might take some of the tedium out of things. I also want to point out a mistake I made on this slide that I caught later on. You can't have int columns in your ML.net models. ML.net likes 3 types of data. It likes strings, it likes floats, and it likes bools. Anything else, it really doesn't support very well, at least at the basic level. You can treat an int just like a float, and it's fine. So the fix for that was to declare those columns as floats. But you're going to run into some runtime exceptions if you try to run things with ints. So just keep that in mind. It'll tell you they need to be a single. Well, a single in C# is just a float. You can use capital S single and it'll be happy to, but most of the time we just say float. But just understand that when it's complaining about it must be single, it just means a float. So once you have your model class, that's when you need to go in and actually create an ML context. That's the context to object is really the main entry point for ML.net. So we're going in and we're creating our context object. And then we're going to load up our data. So we're going to say context.data load from text file. And we tell it what each row should be represented as. So here I'm telling it, hey, put this thing into a car info file, car info class. And this is going to create an iData view representing all that data we loaded up. I need to tell it where to find that data. So I give it the path parameter, telling it, hey, look in the data directory, find my car data CSV. Remember how I had it copied to the output directory? Well, this is why, because it actually copies it to the output directory and it can load it from that file. I tell it that this is a comma-separated value file. The default delimiter is a tab. So if you're trying to work with tab delimited files, you might not need to specify the separator character, but for CSV you do. If you have a header, meaning the first row is just the names of the columns and not actually specific data, you'll want to set has header to true, defaults to false. And then finally, if you expect to see any sort of commas anywhere in your data, you need to have allow quoting of true. Otherwise, it's going to see those commas in your strings as commas for the CSV, and it's going to get very, very confused. You might not encounter this, but I've encountered this on every machine learning experiment I've needed to do. There wound up being strings with commas in them, and turning this allow quoting on was fine, and that was how we fixed it. Next thing you need to do is you need to go in and create and configure your machine learning experiment. This does not run your experiment. We're just setting up information about your experiment. So every task in AutoML works about the same way, but the class names are different. For a regression experiment, such as predicting the ESRB, MSRP. For predicting the MSRP, we are using regression experiment settings. So we're creating a new instance of that. We're configuring the optimizing metric, which I'll talk about in a second, and then the max experiment time in seconds. Microsoft has some helpful guidelines around the max experiment runtime. So if your data set is under 10 megabytes in size and not very complex in its nature, 10 seconds is a good time to train. And then it kind of scales up a little bit based on your size of your data. Now, our data set here is 1 megabyte, so 10 seconds is just fine. You can probably be fine with 1 or 2 seconds. But 10 seconds isn't very long to wait in just a training scenario, because remember, this is not a production scenario, we're just training our data. The optimization metric, this is where we are going in and telling it, hey, how do I need to determine what the best machine learning model is, but what am I using to compare? There's a lot of metrics associated with every experiment type that you're going to run. Regression metrics tend to be around predicting a difference, so a difference between like the predicted value and the actual historical known value. Mean absolute error is a good metric to use there. There's also R squared and other things. You're going to have to dig into what some of these metrics mean for your specific machine learning tasks. But once we have our settings, we then go into context. Remember, that's our ML context .auto. And then we're calling it create blank experiment. In this case, we're creating a regression experiment. So we say create regression experiment, and we provide it a regression experiment settings. And with that, we have our configured experiment. It's not been run, but our experiment is ready for us to run it. So this is how we configure the thing that we're about to do. Most important settings are lines 4 and 5, the optimizing metric and the max experiment time in seconds. For starters, just default to 10 seconds. You're probably going to be okay unless you're doing something massive. Once we have our experiment, we can now run it. And this is the part where we're going to feed it our data. So we're going to store the result of our experiment, which it's a regression experiment, so we're going to store regression metrics by calling experiment.execute. When we call our experiment.execute, we need to pass the data that we loaded. We also need to tell it the name of the column that we're trying to predict. We're trying to predict the MSRP column. We could have tried to predict the make or the model of the car as well. We could have trained a model around that. That would be more of a classification task than a regression task. But a regression task might have been to predict the horsepower or city mileage based on the MSRP and other factors. But here we're trying to predict the MSRP, so I'm telling it the name of the MSRP column. So name of is just going to replace it with a string, really a string MSRP here, but this is a compiler-friendly way of doing this. And then we're going to go in there and actually run it. So this lines 2 and 3, this is going to stop for about 10 seconds because that's our training time. And it's going to wait synchronously for this to complete. AutoML experiment executes are synchronous, so that's something to keep in mind. You might want to do them on a separate thread if you're running a user interface application. You might want to, it depends on how much you care about the user experience. My training applications tend to be console applications, and it's just me looking at them. But keep in mind that these are synchronous for the training process with AutoML. When we have our completed result, we can take a look at the details, and that's going to give us information on all the models that are evaluated. That's usually too much information for me, so I tend to ignore that one. But I look at the best run, and that gives me details on the specific run that was the best performing one. This is my best performing model. If it might have evaluated 12 models and one of them performed better than all the others, that's the one I want to go with. I want to go with the optimal one. How do I know the optimal one? Well, based on the optimizing metric. So the one that has the best mean absolute error for me, that's the one I'm going to go with. And then you can take a look at validation metrics on that best run. So that best run is going to have information about why it was best. And with that information, we can go in and we can take a look at all these various machine learning metrics, such as R squared, mean absolute error, mean squared error, root mean squared error. There's so many different metrics per task, and you really do need to dig into them a little bit more. but this gives us some ways of seeing how the model is performing and various aspects or facets of that model's performance. So we can look at this and say, hey, is this a good model? Is this a bad model? Do we like this? And if we like it enough, you might choose to go out and deploy it. Okay. So let's say we want to deploy this. Well, next thing we need to do is we need to create a class to represent our score. The score is really our the prediction, the MSRP that we are predicting here for our cars. So with our score, this is the predicted MSRP. Very simple class. We actually don't even need that using statement on line 1. I put it in there out of habit. But with that model, or with that class, we can then create a prediction engine. So this prediction engine is going to take a car info. So this is information about a car we've never seen before. It's going to take, and it's going to spit out a car prediction. And so this prediction engine, predictor, is going to be equal to whatever we just create. So we're going to call it context model, create prediction engine, and then we're going to tell it the transformer. Remember, transformer is a model. So we're going to take the model from our best run, this is the one that we just trained, and we're going to give it some information about the schema. I think that schema information is usually optional, but it does tend to speed things up if you can provide it. But we're going to create a prediction engine, we're going to give it the schema, and we're going to have it ready to go. And once we do that, then we can basically call predictor.predict and give it information about a new thing. So it has never seen this car before in its life. It doesn't know anything at all about that car, but it should be able to call to generate a car prediction from it. And from that prediction, we can predict the MSRP value for that car. So that's a lot, but it's not as much as it could be. We didn't need to figure out which model or which algorithms we're trying to use. We didn't need to tell it which hyperparameters for those algorithms we needed. We're just telling it the task that we wanted and the types of classes that represent the inputs and the outputs. The rest of the syntax is sort of learning ML.NET's dance. It is a bit verbose sometimes, but it works. And it requires not a lot of learning from you, which is nice. Once we have our trained model, if we like that model, we can then save it to disk. So I can take that model and its schema, the schema for the data it was trained on, and I can save it by calling context.model.save, and I tell it the file I want to save it as. So here I'm saving it to mymodel.zip. And I can now close my application and shut off my machine, or maybe send my model.zip, put it out there on OneDrive or somewhere else, and my coworkers have access to it. And what they can do is they can go out there and they can start up their production application, whether it's ASP.NET or something else, and they can say context.model.load. And they'll say mymodel.zip, and we have to do some weird things with schema here too. Not wild about some of the syntax here. I might write a wrapper around this at some point or another, but it's working just fine. You get to learn the song and dance of this and refer to your own notes, and you're going to be fine. But this is how we load a pre-trained model. This operation takes a little bit of time, but not nearly as much time as the 10-second operation to train the model or whatever it might have been. Okay, so that is a sample from regression. But we're talking about ESRB rating predictions, so let's talk about ESRB rating predictions. So if MSRP prediction was a regression problem, ESRB rating prediction is going to be a classification problem. For those of you who are not familiar with ESRB ratings for video games, ESRB ratings, it's the Entertainment Safety Ratings Board, Electronic Safety Rating. It's been a while since I wrote papers about the ESRB, but it's a system for creating video game ratings in a way that's exposes sensitive information to parents and buyers. So you don't want to play a game that might have things that trigger you. You don't want your kids exposed to certain things in video games. That's what the ESRB rating boards are for. They categorize each game based on the contents of the game, They indicate whether or not something is present in that game, as well as they give it an overall ESRB rating. That rating is going to be early childhood, everyone, which apparently everyone is not early childhood, which is kind of funny to me. Everyone 10 plus, so this is everyone, and then it's again not quite everybody, but pretty close. T for teens, so 13 and up. Mature 17 plus, and then adult only, and then rating pending is just it hasn't gotten the ESRB rating yet. But if you use this app, you have a pretty good idea of what your ESRB rating might be. So the idea here is that we want to take a look at a video game that has not been released and look at historic information about video games and predict the ESRB rating or ratings that it is likely to receive. This is a classification problem, but specifically this is a multi-class classification problem. Binary classification is something like whether or not Die Hard is a Christmas movie. Again, it is. It's something about whether or not a mole is cancerous, whether a loan should be approved or rejected. That's binary. It's one of two things. Multi-class is 3 or more categories. So ESRB, it could be any one of these, right? But it's going to be only one of those. It's not going to be multiple ones of those. So it's figuring out what category something belongs in. Okay. So first thing I did on this project is I went out to Kaggle.com. Again, they're not paying me, but it's really where I go for all my data because there's so many good things. And I found an ESRB game data set. And it seemed to meet my needs, so I downloaded it and I added it to my project. Whenever you're starting a new project, I would go out there and go find a data set that meets your needs, unless you have some data already. In fact, looking at data sets you like can give you ideas for more projects. So let's jump into this. We're going to jump into Visual Studio and we're going to tour this application. This is a little bit more of a polished example versus the earlier examples I showed you. All right. Okay, so I am in Visual Studio 2022 Community Edition, and I've got a number of things here. And the first thing I want to show you is my Matt Eland AI MLNet ESRB Predictor console app. This is a console application that has a number of factors for it. It's got our ESRB and ESRB test CSVs. They're comma separated value files. If I look at this, we can see the first row here is the title of the game. Then we have the console it was released on. We have the alcoholic references, animated blood, more information about various types of things that may be present in the game. And things, again, are separated by commas, separated values, and each row is separated by a carriage return or enter. Now note the last thing here is E or ET or M or T. This is our ESRB rating. So the last column we have here is ESRB rating. And so that's what we have available to us. I'm going to zoom in here just to make sure folks watching on mobile can see. But we can see we have E, we have ET, we have teen, we have M. So this data set only had 4. It did not have all of those ESRB categories, but it has 4 of them. Everyone 10 plus, that's ET, T for teen, and then M for mature. And if we run this application, I'll just show you kind of what it looks like, and we'll talk about how it works. All right. So here we go. It says, hey, welcome to my predictor. What would you like to do? And I made this fancy little GUI here. Let's say I want to train a model. So T for train a model. How many seconds do I want to train? 10 recommended. I'll just hit enter to accept 10. And it's going to wait and take 10 seconds. And as it goes, it's telling me the various machine learning algorithms it's trying, how they performed, and how long they took. I forgot I had a breakpoint here. Apologies. And I'll hit continue. And it says training completed. The best algorithm was SGD, calibrated OVA. It's okay if you don't know what that algorithm is. I am early on in my journey into the depths of machine learning, so I don't know what that algorithm is or how it works yet. Before I deployed it to production, I'd probably look at it and get more details on it, but this is the one that seemed to perform well for it. And again, this is the part of the point of AutoML, is I don't need to know what all these things are. It knows about them, and it knows to try them, and it knows how to calibrate them. And this is the one that performed the best with a various set of hyperparameters, which I'm not logging what those parameters are, but they are there. And we can see here we have a confusion table. Remember from earlier, things along the diagonal are good. So these are games that we predicted as everyone, and they actually, the predictions are along the x-axis, and the actuals are on this truth, the y-axis. So this is a game that was everyone, and we predicted it as everyone. So we have 89 of those. But there were games that we predicted as everyone, and they were actually should have been categorized as everyone 10 plus. There's 4 of those. There was also 2 games we predicted as everyone, but they actually should have been teen. So that's a whoopsies on our part. And so you can see, we're pretty good at predicting E for everyone. And if we predict it's E for everybody, we are 93% precise. Our precision for that estimate is 93%. Now, if a game actually is E, most of the time we're going to predict it's an everyone, but sometimes we predict it's everyone 10 plus, and sometimes we predict it's a T for teen. So our recall, this is how much we can recognize it for what it is 89%. So a little bit worse than our precision. So we might miss an E more than we would affirm it. So you can kind of look at these 2 scores in tandem. They're very helpful for looking at how well your model performs. For example, I can see here that this model performs very well for recognizing these E columns, but it might not perform that well for things related to T for teen. So when I predict something is T for teen, there's a big chance it might be T for teen, but there's 5 of these occurrences where it actually should have been everyone, 14 instances where it should have been everyone 10 plus, and then 34 instances where it should have been mature. In fact, the engine is not very good at all at recognizing scenarios where things should have been mature. However, if something is mature, we are never categorizing it as everyone or everyone 10 plus. So that's okay. At worst, we're calling it T for teen. So this model seems to be performing pretty well to me. It's not perfect, but I actually suspect that it's not possible to have a perfect model in this data set, just because inconsistencies of how people have rated games over the past. Okay, so now I can save the model to the disk, so I can hit S to save it. It's now saved. I can hit P to predict ESRB ratings, and it's going to go in there and it's going to try a bunch of hypothetical games. So here it's predicting teen side scroller. It's going to predict something for Kinda Sus, which is a game I made, and it says Kinda Sus. That's an E for everyone game. It's pretty sure about that. It's 50% sure that it's an everyone game. It's 38% sure that it's everyone 10 plus. It's only got a 3% chance it's a mature game. So it's kind of interesting. So you can see how it's performing. And we'll try a more precise example at the very end of this talk as we get into deploying some things. But this is how that's working. Now I can quit. And just to demo, I'm going to launch the application again. And if I try to predict right now, it's going to say you must train or load a model before predicting ESRB ratings. So if I choose to load the last saved model, that took, half a second. It was a little noticeable lag, but it wasn't long. But now I can predict, and I'm getting the same values out. So that's great. That's exactly what we want. And if we look, we can see that in the output directory of this, we should have are zip files, our model.zip. So there we go. That's the compressed machine learning model that we created, and you can poke around and see how that's working and how the transformers that are part of that actually work. Now, I don't understand a lot about how that's structured, but it's there for you to look around with if you want. So let's take a look at the class that I built to actually handle the predictions. This is my ESRB ESRB rating predictor. This is just a plain old C# class. I have using statements for Microsoft ML, AutoML, and data. And the first thing I'm doing is I'm creating a new ML context. I'm storing it in context. This new parentheses thing, that's a C# 10-ism. That's the same thing as if I had written new ML context. So just a little bit of a way of making it a little bit less verbose. I have some fields here to store the model and schema of the data, as well as fields for the predictor. I'm going to ignore the little tooltips here as we go. I have a train model method. This method takes in information about the training file and the validation file. So this is a data set that actually comes with two files, one for training and one for validation. And we're going to load them both up and provide both of those to ML.net. By providing ML.net, or AutoML rather, a separate training file and a validation file, you actually speed up the training process significantly, like just orders of magnitude faster. So we tend to split our data into two separate bits so that AutoML isn't splitting into two parts on its own. Next thing we do is we are going to go in and load our training data. And really this is just the same parameters as we saw with the regression. Important things here are allow quoting and has header and the separator character. But we load both our training data and our validation data. Training data is what ML.net actually uses for fitting the model to the data, and validation is what it uses to verify how well the model performs on data it's not seen before. Next thing we do is we're configuring the experiment settings. Now note here that I'm creating a multi-class experiment settings instead of a regression experiment settings. This is because I want to, we're doing a multi-class classification experiment instead of a regression experiment. Otherwise everything's about the same. I'm working with multi-class classification metrics, and I can see those metrics are going to be different than they're going to be different than the regression ones because we measure our classification algorithms differently. I'm then passing in a parameter called seconds to train. That's a parameter that came into the method that the user specified. So in my case, I trained it for 10 seconds, so 10 was the value we used. I'm then creating the classification experiment using context auto, create multi-class classification experiment, and then I am executing that experiment. I'm running that experiment. We're going in, we're getting the training, we're passing it the training data and the validation data. You don't need to pass it validation data at all, but it's much faster if you do. Label column name, so I'm telling it the thing I'm trying to predict. I'm trying to predict the ESRB rating. And then I'm going to give it a progress handler. We'll come back and look at that in a bit. But this is something that's going to report the progress of it as it's training. If you remember when I ran the application, it gave me, 1, 2, 3, 4, 5, how it was doing as it was trying all those different algorithms. So this progress reporter is what lets me do that. And that's a class I had to create, but it's a very small class. Once I have the results, it's stored in this result variable here. And then we can then go in and work with it and use it. Okay, I create a predictor so I can use it later on, and then I'm just returning the best results. This comment here is no longer relevant. It was relevant for a prior version of this. So that's train model. Now, how we predict things is something's going to call classify game. This is a method I created, and it's going to pass in information about a game. I'm making sure that game is not null. In C#11, I could just type in game bang bang here. So that's where Sharper is getting in my way there. But you could type in 2 exclamation marks after that in C#11. So that's an interesting development there. But I'm then taking my prediction engine, that's the one that we built in our train model method, and I'm just calling predict. And it's going to spit out an ESRB prediction class. This class contains an ESRB rating. This is the label that we were predicting, so I'm actually aliasing the predicted label here as that. And an array of floats. This is the confidence of each one. I added in a derived property, so just giving me the confidence it has in the ESRB rating. So this ESRB rating is the one that has the highest score, and the confidence is the confidence it has in that score that is assigned. So, for example, if it said I'm 58% sure this is an E game, then confidence would be 58% or 0.058. Sorry, 0.58. But we get back that prediction, and I'm then wrapping it into a new class here called classification result that contains information about both the game and the prediction. You don't need to do this. This is something I needed to do for part of how I was using this in my application. You could just return the prediction. You could do whatever you wanted to do. By the way, I will post information about the source for this in the video description, so you can take a look at this offline and just learn what you can from it. Classifying games, classifying video games. So, video game classification. So this is really the same thing as what we were doing before with classify game, but now we just have a for loop, a for each loop. And for every one, we're making a prediction, and we're returning the result. So we're adding it to an enumerable that gets created as we go. So single endpoint, multiple endpoint. I shouldn't say endpoint here, but method or API. I have methods here for loading and saving our models. Very easy to load your model. You just say model equals context.model.load. You tell it the file name, and then you can store the schema if you want to. You have to use out here. I do wish the return type was a compound return type instead of making me use out. I always feel like I need to shower after I use out, but that's where we are here. But once we have our model loaded, we're then creating our predictor. It's the same call to create prediction engine. We're passing it in the schema and the model. I don't believe create prediction engine needs a schema, but I believe it helps it. Save model. Save model here is the opposite. We're just calling context model save, and then that's just taking care of the model saving for us. So this is everything related to machine learning around ESRB rating prediction in one single class. And that's really handy because that lets us build larger applications. So I can go into my program and we'll take a look at how we're using this here. So I've got an ESRB rating predictor and some menu code. But if I wanted to train my model, well, I'm just calling handle train model. It takes in the predictor. And then we are just doing some training here. We're calling predictor train model. We're passing in the seconds to train and the two data files. When it completes, we're saying, hey, here's your best algorithm. Here's the validation metrics associated with that. Confusion matrix is wonderful, and I can actually just call get formatted confusion table and put all of that in a console write line, and I got that wonderful little display that we saw earlier with the confusion matrix. Handle save model is about the same. We take in a model file and predictor. So string is the name of the model file. We're just going to do a save and save that model directly to disk. We got to catch exceptions and deal with them because a file might be locked. We might have run out of disk space. We might not have permissions, whatever it might be. Same with load model. We're just calling predictor load model, and it handles the internals for that. And then prompt for seconds to train. This is just a little utility method to get input from the user. So not going to go into that one too much. But as a result, we have an application here that's able to work with all sorts of things related to machine learning. A lot of this stuff is inside of this Matt Eland AI MLNet ESRB Rating Predictor Core, which is a .NET Standard project. But I have information here on the prediction, which we saw earlier. We looked at the predictor in depth. The classification result just stores the prediction and information about the game, and it has some additional properties. This mostly exists for use in the web service project, which I'll show you in a second. Game information. This is a big file. This represents a single row in this comma-separated value file. And we can see we have load column, all of these things. All of these things are features that are part of our ESRB project. And there's too many here, and I had to type these things out manually. The very last one is our ESRB rating column, and that's the thing we're actually trying to predict. So there's a lot of Boolean columns here. If I had a numeric column, it would be a float for a single. So bools, strings, and floats tend to be what it can take in. Last file I want to show you is the multi-class console progress reporter, which is a mouthful. But this is a class that implements the iProgress interface around run details of multi-class classification metrics. Things I'm glad I don't have to say a lot at parties. But this is going to report the progress of a multi-class classification run via the call to report, which is really the only thing on that interface. And so I'm checking to see if the validation metrics associated with the run are null. If they are not, then I'm logging information about the run. If they are, then that really indicates that the run was being aborted because we ran out of time. We reached our elapsed time, and so I'm just logging that. I could just choose not to log anything because that's not going to be one that we're going to go with, but I'm choosing to log that it was evaluating them. All right, so that's the console application. Now, in the real world, you're going to wrap this up into an API or another project. So let's take a look at a .NET 6 minimal API project. This is an ASP.NET API project, but it has a single file here. It's got program.cs and it's got model.zip. Everything else is sort of vanilla ASP.NET. Model.zip, that's our pre-trained model from a prior run that I did. It was a 10-second training run. And program.cs is just, it's 25 lines of code. And we can see here, I have my import statement, or sorry, using statement. I've been doing too much Java recently for work. We're then creating our web application builder. This is auto-generated code, by the way. Almost all of this, actually all of this here is auto-generated code when I create my new project. But it's setting up Swagger and Swagger UI for development. And then I'm going down here and I am creating an ESRB rating predictor. Okay? This is the class that we looked at in depth, and we're telling it to load the model. This is the model that we deployed our web application with, the model.zip. And then we're just telling it what endpoints exist. So when you see a post request, I want you to map it to ESRB rating predictor as my URL. It's going to take in game information from the body of that post request, and I want you to call classify game on my predictor and return the results of that in a 200 OK response. This is the minimal APIs that are new in .NET 6. So if I run this, come on now, we can see the key thing here is I created this ESRB rating predictor. When my application server loaded, I loaded the model, and that just grabbed it from disk, and now we have a trained model available for us. And I can run it, and it's going to open up a web browser, which I will move over to this screen when I can. All right, so here's my web browser. It's showing me my Swagger UI. This is only in development, and it tells me this is the kind of message it might take in and the kind of response I might get back. So let's click try it out, and it's going to generate a title for us, just a JSON to represent this. So I'm going to say CONDG YouTube edition. Let's say yes, this is a console game. It has alcohol references. It does not have animated blood. Does not have blood. Does not have blood and gore. I really hope. Cartoon violence, sure. Crude humor, sometimes. Drug reference, well, I guess it does now because I just referenced drugs. Fantasy violence, no. Intense violence, oh, I sure hope not. Languages, sure. We talk about C# and F# here. Don't really talk about VB too much. Lyrics, mature humor, yeah, you got to be kind of matured in order to understand about F#. Mild blood, again, I hope not. Be careful. And we'll just kind of leave the rest of these default. So most of them are defaulting to true. That's just what the thing was doing. And it's going to generate some sort of response for us. No, I'm not going to leave these as defaults. No nudity evolve at CONDG. All right. So, I'm going to hit my execute. Makes a request. You can see details about the request if I was to do it in curl. Got back a 200 OK. CONDG YouTube edition is rated T for teen with a 95.9% confidence score. And it has some very low probability. You can see the E exponential notation that it was rated everybody. Very low probability was rated for everyone 10 plus. And a 4% chance it was rated mature. So, all right, it's pretty sure that we are a T for teen user group. So I will buy that. I'll allow that. My key point here is that it's pretty easy to create a new .NET project. Almost all of this was auto-generated. All I had to do was add a reference to my my core project, ESRB rating core, create a new instance of predictor, load that model that we had pre-trained, and then just map a new endpoint to it. So once you have something like this trained and ready to go, you can use it pretty easily in an existing web application. Now, most of the time you're going to be worried a little bit more about error handling, authentication, things like that, but you can kind of see how this fits into your normal flow of things. If you were running more of a traditional ASP.NET non-minimal API kind of application, you're going to have a startup file, and you're going to basically use an add singleton to create and configure your model, and you'll use dependency injection in your controller to load up your ESRB rating predictor when your controller loads. So it's the same concepts, you're just taking advantage of dependency injection for that. So, all right, so that's ML.NET AutoML in a nutshell. I didn't need to learn a ton about the various algorithms to do things. It just sort of let me do them. So closing up here, let's talk about how you can get started, because I do want you all to blast off and be able to be awesome people. I would encourage you to go out there and find a machine learning task that interests you, or find a data set that interests you. One or the other. But if you find an interesting data set, say, okay, well, what can I do with this data set? What categories can I predict? What numeric values can I predict? If you find a if you're really interested in doing a classification run or a recommendation run or something like that, you say, okay, fine, I need some specialized data for this. What data would be good for this? I really wanted to do a classification run, and it wasn't until my wife and I got into a discussion about Die Hard that I had an idea of what I wanted to do with it. I didn't use ML.NET for that, or I would have showed you that today, but that's okay, another day. So once you find your data, go out, try to build something in ML.NET. You're going to have to refer to some existing code with ML.NET. It's just the syntax is a little verbose with the generics, but it's pretty good, and you can discover a lot of things on that context object as well. Google stuff, reach out to me on Twitter, whatever you need to do, but build something awesome. And when you have something awesome, tell other people. That's my main thing. So if you want some additional resources, I highly recommend Microsoft's information. Go out there to .net/ML for their mains page. You can look at all their code for all the projects on GitHub. I still need to go through every file in ML.NET. I'm really invested in the framework, and I want to learn a little more depth. Microsoft's documentation is fantastic. It'll walk you through a lot of machine learning basics, even things not related to ML.NET, as well as all the little things around how we measure this stuff and the metrics associated with things. If you're curious about data science in general, especially on the Microsoft stack, subscribe to me on YouTube. MattOnDataScience.com will take you to my YouTube channel homepage, so you can find a bunch of other stuff. I'm also thinking of creating an ML.NET course on Udemy. So if that's something that interests you, ping me on Twitter, and I'd be glad to get your feedback. I also write sometimes on AI concepts at accessibleai.dev, and in fact, I have a whole article out there on accessibleai.dev on this whole project. So you can take a look at that. If you're more of a book person like I am, there are two books that I would recommend for you. The first is a packed book on hands-on machine learning with ML.NET. It can be a bit code heavy, but it's a good book. The second is actually still in the process of releasing. The Kindle version released Monday of this week, and I'm on chapter 4 or 5. But the print version will come out in a few weeks, I think, and that's Programming ML.NET by Dino Esposito. Now, Dino Esposito and his son Francesco Esposito, they have another book out there on learning machine learning. I do not recommend that book as a first book because it gets very deep into the mathematics. So far, I've been very pleased with Programming ML.NET, and it would be my number one recommendation so far, but I'm not finished reading the book yet. And again, if you build something awesome, just tell me. Find me on LinkedIn, hit me up on Twitter, send me an email at matt@mattondatascience.com, and I'd be delighted to answer any questions you have. So I hope you learned something from this talk. If you're curious about more, let me know in the comments, and I will be glad to engage with you or produce more content on that area. But happy coding, and I appreciate you.